Apparently happens when you get older. 60 years old. Not 60 years old. It's like I feel like Tom is like a they say that I was like kind of serious but ready to party break. It's not bad.
But it's hard to so I was like, oh,
Alright.
There we go. Alright. So how was the homework assignment?
Difficult at first.
Difficult at first. Okay, very good. So if it's difficult at first, it means you're trying to make the connections between all of the components.
Yeah.
So most of the time, it really helps to start from one end. You can either start with the objective, which are the sum bits and also the carry out, and try to work your way backwards. Or you can start with what is given to you, which are the x, the y, and also the carry in, and then try to work your way forward.
Yeah.
So either way is okay, or you can try a little bit of both, and they should meet somewhere in between. Okay. So let's go ahead and take a look at the solution of today's of the homework assignment that was due a minute ago. And do you guys remember that I recommend the use of a multi-bit gate, like a multi-bit AND gate, a multi-bit OR gate, and stuff like that? Okay, and also the use of subcomponents. Okay, so all of those will be helpful. Okay, I have the solution already, by the way, but I'm not gonna just unlink, just unhide this link here. 4-bit carry look ahead adder. I'm gonna show it. You can just download it at this point and be able to take a look at my solution. But instead of just letting you guys look at the solution, I'm gonna work on it today in class and after I talk about the next homework assignment, because I do want you to kind of keep the new homework assignment in mind as I explain the solution to the current homework assignment. Okay, and there's a really good reason why that is the case. I'll let you guys figure that part out. Okay. All right. So we'll start with the new homework assignment. This is due in a week. I really doubt that it will take you more than, I don't know, half an hour to get this done. Okay. So we'll take a look why. So your new homework assignment is not an adder. It is a subtractor. It still has the look ahead mechanism. This time it is a borrow look ahead instead of a carry look ahead. When you look at this description here, I basically just globally replace carry with borrow and adder with subtractor and stuff like that. I might have a few places where I forgot to make some changes or have a typo like borrow, like that. But otherwise, it is the same kind of deal, except we are subtracting 4-bit from 4-bit instead of adding 4 bits to 4 bits. But because we are adding, because we are subtracting, it is important to denote, which one is the minuend and which one is the subtrahend. Okay, the minuend is the one that is you're subtracting from, and then the subtrahend is the quantity that you're subtracting from the other one. So in x minus y, x is the minuend, and then y is the subtrahend. Okay, just want to make sure that those terms are clear. Okay. All right. So other than that, it's the same homework assignment, and then you have one extra thing that can potentially be helpful. You can create this project from scratch. Okay, if you choose to do that, that's fine. You can use your adder project as a starting point, or you can use even my solution to the adder project as a starting point. So what I'm going to work on right now today, you can use it as your own starting point for this homework assignment. Is that okay? All right, okay. So let's go ahead and get this done. And I also found this resource here. It's called Logit Sim Evolution. Apparently this is a slightly improved version of Logit Sim, so it may not crash as much, and it has some newer feature. I have used it already myself. Yep.
Are you recording?
I am going to check. Yep, looks like it is recording, and the voice is getting recorded as well. So I think we're good. So I'm going to download this one. Logit Sim Evolution. Someone watched too much of a movie. Especially that vampire movie series. Yep.
Underworld? Underworld?
Yeah. Yeah. Interestingly, my son is doing a research on a particular genetic defect that might have caused people to be mistaken as quote-unquote vampires. It's a condition where people will be sensitive to sunlight or even artificial light. Their gum would actually recede as well, so they would appear to have fangs because your teeth is more exposed. You don't have as much gum to cover the teeth. And they will also have bloodshot eyes and stuff like that. Basically things that we normally associate with vampires or even werewolves, because they just don't look like a normal person. So he's doing a research on that topic, which is kind of interesting. I'll be sure that he adds evolution to his presentation too. All right, so let's go ahead and start up that particular program, Logit Sim Evolution. It looks exactly the same as before, except it has like one or few more components like FPGA menu. I don't think we'll get to FPGA in this class. If we do, it will be really cool, kind of awesome. But if we don't, it's not a big deal. Okay. All right. So let's go ahead and get started with this project. First thing first, we'll pick out a few pins here as our inputs. Okay. So let's see. We'll label the first one X, label the second one Y, and the third one Cin. Okay. And X, Y are both going to be 4-bit wide. So we make it 4-bit wide like that. Okay, all right. So first thing first, we know that we need the G terms, the P terms, and also the W terms, okay? So let's go back to the notes and just kind of find out, okay, what are those terms? All right, so let's close this, go back to the notes. Oh, we're in the assignment. That's okay, we can get out of the assignment. Go back to the previous slide, which I think is here. Okay, that's great. Okay, so what we want to do is to figure out, okay, what are we going to do with the input bits, the X and the Y's, okay? That's the first thing we want to do. So the first thing we do is to say, oh, let's Wi be bit I of the intermediate sum. And because they are the intermediate sum, according to the notes, we define Wi to be the R function, which is just an exclusive OR applied to Xi, Yi. So that means W0 is Xi exclusive OR Y0, and so on. Is that okay? All right. And further down in the notes here, we also define what is G and what is P. Okay. So we define G of I to be Xi, Yi, which in this case means Xi and Yi. We define Pi to be Xi plus Yi, which in this context means disjunction. So Pi is Xi or Yi. In other words, we have all of these terms already, W, G, and P. They are ready to be computed as soon as we have Xy. Is that okay? And better than that, okay, they are all bit coordinated. In other words, W0 only relies on X0, Y0. G0 only relies on X0, Y0. P0 only relies on X0, Y0. And they're the same way with the other 3 bits as well. So this is a good way to look at it, and because we can now use a multi-bit gate so that we don't have to split the wires unnecessarily. Is that okay? So let's go ahead and check out how we can do that. Okay, so let's switch back to Logit Sim. I'm going to space these things out a little bit because I will need a little bit more space, but not as much as most people think. So we take a look at the gates and go like, okay, let's deal with, I don't know, W first, okay? So I already told the class that you can use an exclusive OR gate to compute the W's instead of using two AND gate and an OR gate to do that, just use an exclusive OR and be done with it. Okay, so we'll go ahead and look at this gate. I personally do not like the gigantic, gate symbol. I just make it smaller. But the most important part here is to change the data bits. Instead of one single data bit, it now has 4 data bits. So the 4 data bits is important because it is matching the width of the input pins. Because X is an input pin that has 4 bits. It matches the gate now. Is that okay? So we'll go ahead and connect these two. And I'll label it too because I want to tell you what the output of this gate is for. It is our W. Okay. So we'll hook up these wires. And you can see that they are not causing problems. The wires are not causing the orange notation. The orange notation happens only when you have something on one side that only has like 1 wire or 1 bit, the other side has 4 bits. If the number of bits do not match, then you have the orange notation. But since they're all 4-bit wide, we don't have a problem. Okay. Are there any questions about a multi-bit gate and how it operates? You guys are lying. Or some of you at least. There exists at least one of you, who is lying, because I know not everybody understands the idea of what is a multi-bit gate. Okay, so a multi-bit gate is basically saying, let's take bit 0 of both of the inputs, and that becomes bit 0 of the output. Let's take bit 1 of both of the inputs, that becomes bit 1 of the output. That is a multi-bit gate. Okay. So what we'll do is we'll check it out. Okay, you can actually run this, by itself. Okay, and it works. So we'll check out. This is exclusive OR, which means if the bits are different, the result is a 1. If they are the same, the result is a 0. So we'll check out all four possible combinations. Okay. Okay, and you say, I don't see a single thing here. Okay, I don't see the result. Well, click on the output. That shows you the actual output. Okay. So do you see how 0 exclusive or 0 is 0? 0 exclusive or 0 is 0. The bit position corresponds. Is that okay? Are there any questions about this? Because this is really, really important. When you perform bitwise operations in C and C++, you are performing multi-bit Boolean operations. Do we have any questions about this? The /3 is the decimal representation of 0011. So that's just 3. So for what we are doing right now, we can ignore the decimal representation. Okay, what about the next one? The next one is 1 exclusive or 1 is a 0. 1 exclusive or 0 is a 1. 0 exclusive or 1 is a 1. Okay, so with one single gate, I have just computed all the 4 W individual bits. Okay, it makes the design a lot cleaner. Okay, so with this kind of technique, I can also do the same thing with the P and the G terms. So the G terms are basically a conjunction. So I would do exactly the same thing, make it a narrow gate, and change the number of bits to 4. Okay, I will put it here. And make the label correspond to what it's doing. This is computing all the G terms. And to compute all the G terms, we're just going to feed the input into here. And now we have all the G terms. Well, let's double check because I don't want to, I want to make sure this works. So let's go back to simulation mode, click on this wire, and see whether it makes sense or not. This is a conjunction, this is AND. 0 and 0 is 0. 1 and 1 is 1. 1 and 0 is 0. 0 and 1 is 0. Okay, so that works out too. And now we can pull a OR gate because the OR gate is needed to generate all the P terms. So do the same thing over here, change the label to P, and change the number of bits to 4 again. So same thing. So now we have all the P terms. Now they're all bundled up into one single wire, which means I still have to split that at some point, but at least I don't have 4 individual gates to do it. I just have one single gate to perform all the operations. 0 or 0 is a 0, 1 or 1 is a 1, 1 or 0 is a 1, 0 or 1 is a 1. Okay? Are there any questions about the use of these multi-bit gates? Do you see how it is kind of handy? Okay, all right. Okay, so with this, I have all the terms that is readily to be computed. Now it is time to actually deal with the carries, okay? So with the carries, I personally would prefer to use subcomponents. So I would go to project and add a circuit for each one of those carries. Okay, so each subcircuit would only deal with one particular carry. So we'll deal with C1 first, okay? And obviously, because I have very poor memory, I cannot remember what C1 looks like. Well, it's already in the notes, so we can look it up. And I think it is, yep, here, right here, okay? So C1 is G0 plus P0 C0, okay? So the first thing I personally do is I just comment it first. So I say C1 is G0 plus P0 C0. Okay. Now I want to make a subcircuit to perform this operation. Now this subcircuit only requires G0 as 1 bit, P0 as 1 bit, and a C0 as 1 bit. But I am going to make the interface a little bit wider than it needs to be, and then I just single out one wire to use. Okay, and there's a reason why I'm doing this. Okay. So I'm going to make the pins kind of the same way as the other one. So I will make this a 4-bit pin, duplicate it, okay, and label one as my G, label the other one as my P. Even though I only need one of these bits, I'm going to have the pin to deal with all 4. And I have one more input pin that is just a single bit of the carry in. But this time I will label that as C0 because the equation calls for that. Okay. Now I need to split these 4 into the one that I need. All right, so let me give it a little bit more space. We go back to wiring, go to the splitter, and I just dropped the splitter somewhere on the screen because I need to tweak it. So I need to tweak the bit width of the splitter to 4 bits because we do have 4 bits coming out of it. And this is the fun part too, because you can change the fan out to just 1. So it only has one single wire coming out. And then you can change bit 0 to none, bit 2 to none, bit 3 to none. So the end result is we have a quote-unquote splitter that really is not a splitter, because I'm splitting, but I'm also cutting off the 3 wires that I do not need, leaving the only 1 wire that I need. Okay, so that really kind of helps to make it look nicer. It is not needed, okay, it's not required. If you don't mind it looking a little bit kind of like busy, you can always split all 4, ignore the 3, just pick out the one that you need. Yep.
Doesn't that make an unterminated wire can cause interference? Or?
If it is an input, yes, it can be a problem, but when it's an output, it's not an issue. In other words, the 3 wires that I am not using in this case, they are still driven by the input pin. I'm just not using it at all. It's kind of like, when you have a subroutine, you have some parameters that are not being used. So that's okay, but it's not okay not to specify a return value when you have a return type for a subroutine. Mm-hmm. All right, so I'm just going to use this technique, duplicate this pin. The duplicate ability is really useful too, because when you have something that's kind of like what you need, you just duplicate it a few times and you get all the things that you need. All right, so I have all the things, all the signals that I need. Now I just need a conjunction and a disjunction. So I just pull a conjunction first. Okay, conjunction, make it a narrow one. And I am doing the AND between the P and the C, so it will be between these 2. The reason why I have a multi-bit input pin is going to be clear in the next step. Okay, and I'm not going to spend too much time to make it look nice. Okay, so I'll just make it look like that. and then the output is my C1. So I pull this, put it here, and label the output pin as C1. There we go. Okay, so now we have C1 as a circuitry done, and I just go back to edit circuit appearance. Yep, go ahead.
Can you go back to that?
Yep.
So how many bits coming out of the 4-bit at 4-bit G0?
Right here we have 4 bits,
But then
but here we only have 1 bit.
So 4 gate is just 1 bit.
Yeah, so there are 4 bits coming in, or there are 4 individual traces coming in, but I cut off the 3 that I do not need and leaving only 1 going out of the splitter. This is just a fancy way to do it. If you don't want to do it the fancy way, you can always kind of do it this way, which is basically just using the one that you need and leaving all 3, the other 3 unconnected. That's fine too. I'm just making it look a little nicer by not even showing the 3 wires that I'm not planning to use. But this is fine too. This is not a problem. Is that okay? Okay, all right. So, so we have GP and C0, and I want to go back and edit the appearance because I am really bad at remembering anything, even if it is my own creation. So I have to remember this is G, and then we have P, and then we have C0, and then the output is a C1, and just move things around a little bit. Yep.
If you label the input pins when you make the circuit,
Yep.
when you use this and you hover over that dot,
Oh, when you
tell
hover?
what input pin it is.
Okay. Yeah, but I'd like to have it visible as well on the component. Okay, just like that. Okay, so this one is done. Next one, I'm going to create the C2 circuit. So we go to Project, Add Circuit, and this time it is C2. And C2 is right next to this. Okay, so it is this particular circuit. So you can see there's a pattern to this equation. So when you have C2, then we have G1, and then G0 P1, and then C0 P0 P1. So there is a particular pattern to it. If you do not see the pattern, it's okay. You just need to go back to the original. You just need to go back to this general equation, expand the terms individually, and you will still come up with the correct answer. Okay, so let's go ahead and make a C2. I wonder whether copy and paste is going to work, so I'm going to give it a try. So we'll do it here, paste. Nah, doesn't work. Okay, C2 is G1 plus P1 G0, G0 P1 plus P0 P1 C0. There we go. All right. I'm going to be a little bit lazy. Go back to the other one and just kind of borrow something here. Okay. Copy. Paste. There we go. So we got most of the important components here. You just have to arrange things a little bit differently over here. So if you don't like this kind of splitter because it looks kind of awkward, you can always make it split just 4-way all the time and use only the wires that you need to use. That's perfectly okay as well. All right. So in this case, we have 3 conjunctions, or 3 conjunctions and 1 disjunction. So we'll go ahead and deal with the conjunction first. And this one needs 3 inputs, so we change the number of inputs to 3. And we'll make it a narrow, just like that. Okay. C0, P1, and P2. P0 and P1. Okay. This one. Here's the other one. And then we need another one for G0, P1. So once again, change this to a narrow one. And it's P1, so this would work, and G0, like that. And then we need an OR gate that has 3 inputs. So we'll change the number of inputs to 3. The first one is going to be G1, which is here. Oh, that's going to look ugly. This will look a little bit better. Like so. And it has one single output pin, which is C2. Okay, there we go. We got C2. So we are done with the second circuit. Yep.
Is there a reason why we have to put in the third conjunction with C0 if it's always going to be false?
It's not always going to be false.
But it has to be P0, P1, and C1 to be true, and C0, but C0 is always false in this way.
Not always, because this is now an input pin, so it can be true or false.
Okay, just in this situation.
Right.
Okay.
But when we are testing it, C0 can be true or false.
Okay.
Now, with any subcircuit, you can always test it as well, because this is testing whether C2 is correct or not. So we can always just test the subcircuit itself without the overall circuit. So you can say, okay, if I have 1 plus 1, which is 1, 0, C2 is a 0, that's okay. That's perfectly okay. No problem. Now it should be a 1. Yep, that works. If I take out these two 1s, it should still be a 1. That works. So I can kind of test it, not exhaustively, but I can test whether it is working or not. Kind of validate it a little bit before I make use of this subcircuit in the main circuit. Okay. All right. So now we can move on to the third one. So we go to project and we add another circuit. This time it is C3. C3 is not included in the notes, so you will have to generate it yourself. So there are two ways to do this. Okay. So let's go back to my notes here. To generate C3, you can use C2 and just say, okay, using the pattern, it will be G2 plus P2 times C2, and then you just expand that, expression. Yeah. So you can do it that way, or you can use, this closed form as well. Okay, if you can read that closed form and understand what it means, you can use that too. Okay, so it's up to you to decide, how you want to generate, C3. I just like to use, these kind of closed form equations. But if you want to expand it, out of C2, that works too. All right, so we have C3. C3 is G2 plus G1 P0 plus G0 P0 P1 plus P0 P1 P2 C0. I think that is correct. Okay. And so once again, I go back to the other circuits to borrow stuff, right? So the idea is, I don't want to do things unnecessarily. So if I can borrow something, from the other circuits, I would just go ahead and do it. So Control C and Control V. Here we go. So we have all the basic stuff here. So it's just a matter of hooking up the wires now. So we have a AND gate. This time we need 4 inputs, and the 4 inputs would be C0 and the 3 P's. 1, oops, 2, 3. Okay, so I'm done with this term. The next one is a G0, P0, P1, only 3 terms. I'm going to go for a smaller one, like so. There's no need to make it look really pretty, as long as it is functional, it is okay. And it has G0, so G0 comes from here. All done. And now we have G1, P0, simple AND gate, or I can just duplicate this one and change it to 2 inputs. There we go. So this one has got G1, P0. So here's G1, and here is P0. There we go. And then we only got 1 term left, which is G2 by itself. So now we can hook up all of these using a OR gate. The OR gate is going to have 1, 2, 3, 4 components. So we'll change the number of inputs to 4, and just kind of stash it, I don't know, over here. As I said, it doesn't have to look good. I'm just gonna be, I'm curious, you know, how many people actually turn in something that is artistic, and how many people turn in something that is, well, let's just say Borg-like. It is functional. It works. It flies. Even though it looks like a cube, it flies in outer space. It's good. Alrighty, so we got this one as C3. Whoops, one more C3. There we go. And I'm just going to test it a little bit too, you know, because I don't want to include something that doesn't work into the main circuit. And because this is C3, that means, you know, to test it, I can put 2 ones over here and see. Whoops. That's not good. So I pulled the wrong G. No, these are G's. Okay, never mind. So they are not the X, Y's, so these are the G's. Okay, that's fine. That's okay. The generate term is okay. All right, so this one is done, and moving on to the last one, which is the messiest one. And if you do it this way, it's not going to be that messy. Okay, it's a little bit more involved than the other ones, but there is definitely a regularity to it. So we'll go ahead and, oh, I forgot to do this. Look at the circuit appearance. But since it's going to be the same pattern, I'm not going to spend too much time to deal with this, other than saying that this is C3, the output is C3, and then the other one is C2. I just need to document, because otherwise they all look the same. I would have a hard time finding out which one is which one, other than hovering over the pins. Okay, one more. This is C4. So once again, you know, I would use, you know, the text tool to kind of enter the equation here, because I can't really flip between 2 screens or some piece of paper, you know, and map the expression to the drawing. I would much prefer to have the equation on the same, you know, in the same document. So it starts with a G3 by itself, G2 P3, and G1 P2 P3, G0 P1 P2 P3, and we have P0 P1 P2 P3 C0. I think that is correct. Does it look about right? Okay. So there is definitely a pattern to it, okay? Because if you work out the first, the second, and the third one, then you will probably notice the pattern and be able to just kind of figure out this one without even referring back to the notes. Okay. And once again, we're going to borrow stuff from the other ones. Oops. Okay, Control C. Go back here, Control V. Okay. This one's going to be messier because, you know, we just have more terms, but that's okay. It's not a big deal. So now we have a 5-input AND gate, which is the worst we get in this particular homework assignment. If you talk to anyone from the previous semester, they would look at this design and go like, wow, you guys have it easy, man. Talk to Shane. Talk to Shane. Shane's gonna go like, wow, you know, he's going easy on you guys. What is happening here? Alrighty, we are almost done. Okay, this is it. The next one has 4 input pins. So with the 4 input pins, we have P1, P2, P3, and then G0. So, okay, how am I gonna make this look good? Okay. There you go. Oh, there we go. There we go. And then it needs a G0. There we go. So we're left with that term. How many people spend a lot of time to make it look good? Okay, so we have a G1 this time. So we have a G1. Okay, that's going to look a little uglier, but that's okay. Okay, duplicate. This time only has 2 input. All right, almost there. So we got a G2 straight across and a P3. Okay, I can tell you from here. And now we just have a G3 by itself. All right. So we have a 5 input OR gate this time. And then the output is called C4. There we go. All right. So we'll go ahead and edit the appearance and just change this one to C4. All right. So we got all the carry bits now. So we go back to the main and we say, okay, so how do we get this to work? We have to combine so we'll have all of these subcircuits. So we got C1 as a subcircuit, C2 as a subcircuit, C3 as a subcircuit, C4 as a subcircuit. This is the reason why I make all the inputs uniform. They're all taking 4 bits as inputs because I can just run what I would call a bus and multi-drop it. So the G's would just multi-drop across all of them. So the G connects to here, connect to here. I don't need a whole lot of splitters anymore. And then the P's would just drop off here, 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 and here. And then the carry in is just going to drop off, at where we need the C0. So one over here, one over here. Whoops, didn't quite make it. Here we go. And one over here. So this is the reason why I make all the inputs uniform, because now I can just multi-drop these wires without all the splitting and merging and all kinds of crazy stuff like that. Is that making any sense? Okay. And trust me, I just did this morning. I didn't actually do this way ahead of time, and have the solution. So when you guys asked me last week, like, how should I arrange these things, I was thinking like, I don't know. I'll let you know when I do it. But that's not part of the grading criteria. There's no artistic point in this homework assignment. Any way you make the connection that is logical and it works, it's good. Okay. All right. So now we have just like 2 or 3 more steps left because we have to combine C0, C1, C2, C3 back into one single thick wire so that we can use another exclusive OR to compute the sum bits, okay? So we need a splitter or a merger in this case. So we'll go up, pick out a splitter, and this is going to be a 4-to-1. So we need to flip the direction. So instead of facing in east, I make it face west, just like that. And now we can merge C0, C1. Now the ordering is important because we need to make sure that we preserve the significance of the bits. Okay, so this is actually kind of important that we keep the order. So now we have, that doesn't look right, does it?
Because your C4 goes directly to C out.
Yeah.
Say again?
C4 goes straight to C out.
Yes, C4 goes straight to C out, but this wire is a 1.
Because you have it
Because you have
numbers already.
Because I have it in the subcircuit?
No, the next
No.
line, no, go back to your main. You have.
Oh, because I already have a test case, it's not 0. Okay, gotcha. Okay, I forgot that I had a test case already. All right, so this is C4, which goes out to the carry out pin. So we just now put pin here, call this carry out. And these wires are going to be important. Okay, these are useless at this point. Okay, we are done with the G's and P's. So we have to combine this, which is the C and the W, so that we can get to the sum. So what we need to do is to duplicate this guy, and this time we call that the sum, so that we take one input from the W. Now this is all in the notes too. I tried to make sure that everything is in the notes. So the sum relates to the W and the carries. Okay, where did I put that? Pretty sure I have it somewhere. Probably earlier. There we go. So all I'm doing is to implement this particular function here. So we got all of these as the carries, put it into this final exclusive OR gate, and then we just have one single multi-pin or multi-bit output pin that we call the sum, and hook it up, and that should be it. All right, so let's test it, because we have one test case right now. The question is it right? Is it correct? So let's see, 0 plus 1 is a 1, 1 plus 0 is a 1, 1 plus 1 is a 0 with a carry, so the carries to the next one, but we do not have a final carry. So that looks right to me. If I put a 1 and a 1 here, that should have an overall carry. So let's try that. Yep, that has an overall carry. So I can just test out a few cases to make sure that it does work correctly. I can also test whether C-in works or not, because I can make one of these numbers just 1, 1, 1, 1, make the other number all zeros so that there's no carry whatsoever. But then when I change carry into a 1, that will change the output to all zeros with a single carry as the carry out. That works too. Frankly, I am kind of amazed that I did not make a stupid mistake somewhere. Considering how many clicks and right clicks there is involved, so I'm kind of surprised that I did not make a stupid mistake somewhere. But that's it. That's your homework assignment. That was due 40 minutes ago. Any questions about this? So once again, if yours doesn't look clean, okay, it's not a problem. If you use individual bits and have a lot of exclusive OR gates everywhere, it's not a problem, okay? As long as you get the idea and the result is correct, it will still be okay. Okay, but I do want to show you this particular solution because the use of multi-bit gates is really helpful in this case. Yep.
If you made just like a C circuit instead of 4 individuals, is that wrong?
They are all different, so they cannot be one single one for all of them. Okay. Did anyone not use any abstraction, and so you have just basically all the gates in main? Yeah. Okay. Did you use a multi-bit gate? So that you have basically wires and gates all over the place?
Like XO, X1, Y1, Y2, whatever.
Okay. That's okay too. Okay, so here's the question. How are you going to do the next homework assignment, the subtractor thing? Okay, so let's go ahead and read the notes on the subtractor because it's right next to this, okay? So we have carry, look ahead, blah, 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 and then we have subtraction, right? So with the subtraction, I go through all the calculations, and then we end up with these two terms. Now, this means that we can just redefine GI to be XI bar YI, which means it's the negation of XI and YI. And we can also redefine PI, so that it's the negation of XI or YI. So you do need to make some changes. There's no quick and easy way to turn your adder into a subtractor, but the changes are fairly minor. Because the way we use this messy thing, in other words, when you look at the actual equation using the g's and the p's, that does not change. Okay? The definitions of g and p change, but the way you structure the p and the g's to come up with the borrow terms is identical to the carry terms. Yep.
So we just need to make a subtractor, right? Just a, because I had mine was like an adder, and then I fed it into a separate like module for each carry, you know. So you just need to make a subtractor to work with your adder program.
You can, well, you have to turn the adder into a subtractor.
Yeah.
So the question is, how are you going to turn an adder circuit into a subtractor circuit? And you know, I can tell you that it's a fairly simple thing. You have to locate certain gates and do some changes to those gates. And change the labels too, because we don't have C anymore, we have B.
Yeah.
We don't have sum S anymore, we have D for difference. But other than that, I would say the changes are very minor. And one big, huge, gigantic clue here, other than just the name changes, there are no changes to C1, C2, C3, and C4 as subcircuits. You just go in and change the labels. But why is that the case? Why is it so easy? It's easy because this term does not change. The way we propagate the terms does not change because the structure has not changed. Yep, go ahead.
You said we don't have to change the C circuit, so you're going to have to change the logic within the C circuit. Like you have to put, for G the term, it's the and, so you
Okay, so
the X, you have to put the little not thing.
let's take a look. Let's take a look at C2, okay? So C2, in this circuit, the structure of the circuit, okay, let me zoom in a little bit so that we can just have a better view of it. Okay, there we go. So the circuitry is reflecting the structure of the expression, right?
Yeah.
In other words, what determines what kind of gate we use here and how they're connected has to do with this, right?
Yeah.
But you remember that in the other slide over here, it means that once we redefine what is GI and what is PI, the term BI is still following exactly the same structure.
Oh, so in your subtraction, instead of making the G just the and of X and Y, you make it the and of X and Y.
Well,
So you have to change this.
you have to change that, yes. I'm not going to say what to change, but you have to change some of those things.
Okay.
But what is coming into here is already changed. Okay, so the structure of these things should not need to be modified. Is that okay? Okay, so one more clue, okay, because I just like to sprinkle some clues in this case. Okay. Until somebody texts me right now and express objection. It's like, Jack, stop, don't do this anymore. Okay. Okay. So when you use an AND gate or gate, okay, I'm not going to use a gate that you have to use. I'm going to use some gate that you don't have to use. Okay. So we're going to use a NAND gate. Okay, cool. Okay, this is a NAND gate. So when you look at the properties of a NAND gate, okay, let's check out every single one of these. Okay. So it has got phasing, which has to do with what it looks like. Okay. Big deal. Okay. So if you want to turn my entire thing from left to right instead of you want it top to bottom, go ahead. It has data bits, which may or may not be something that you want to change. Gate size, just appearance, number of inputs, stuff like that. Output value 0 or 1 instead of floating versus non-floating. Keep it at 0 and 1. Okay, that doesn't really need to change. But when you look at these two, you kind of have to figure out what those two are for. Okay. One says negate 1, which is the top, and the other one says negate 2, which is the bottom. So when you click one of these things, a bubble happens here, and you have to figure out what it's for and how it relates to your homework assignment. So why would you want to have blisters on your gates, right? Yep.
Could you scroll up real quick? I just want to
scroll up.
Yeah, just okay.
Yep. Now, of course, you can always remove these extra stubs and make it look nicer, stuff like that. Okay. So I am, so I'm re-estimating how much time it will take you to get a homework assignment done. And I'm gonna say, including downloading it, editing it, and re-uploading it, I'm gonna say 15 minutes.
But that's if we have this design. If we have our own, crazy design, then it might take some time just to locate those bits that we need to change.
Unless you know how to read the XML file, and then you can find out how to do a global search and replace to negate some of the gates that you need. No, but you can use my design. That's part of the homework assignment, is you can use my design as a basis. So that really should make it a little bit easier. All right. Are there any questions about the new homework assignment that you have a whole week to do? I think the new challenge with this new homework assignment is you forgetting to do it. Because most of you will think, oh, I can get it done in 5 minutes. Text said 15, but that's because it's old and slow. I can do it in 5. So you would think, I don't have to get started until next Monday, or possibly next Tuesday at 3 p.m. That will still leave me plenty of time. And then you forget about the whole thing altogether. That would be the biggest challenge for this homework assignment, is forgetting to do it. Okay. Now that said, it is important to understand how it works. Okay, so even though most of you probably know how to modify this circuit to get it to work, it is still kind of important to understand what you're doing and what is why does it, how does it work? Okay, that is important. So even though the structure is clean, it's easy to understand, you still have to understand how it works. All right. So that is done. And I don't need to save this because it's on Moodle already. If you go to Moodle, this is the right class. And if you scroll down right below the first homework assignment, that's the key.
Oh.
Yep, so that's the key. If you click on it, you can download the file. It doesn't look exactly the same as the one that I just did, but it's pretty close, okay? It's really close. So this is your new homework assignment, due in a week. So now we can get back to signed integer representation, which is something that we did last Thursday. And, yep, okay, that's good. All right, so I did write this entire module, just so that I have the text that I need to get through this stuff. Okay. So we start off with the representation. Okay, how do we represent signed integers? Signed integers are values. They are not quote unquote numbers. They're just values. -1 is a value. -5 is a value. 20 is a value. So the question is, how do you represent those values when all you have are zeros and ones? That's the question. Okay, that really is the question of how do we represent signed numbers? We go through a few things like, okay, what about using just one bit to indicate the sign, and then everything else would work the same way. In other words, we just use one bit to indicate the sign, and then we track the absolute value of the value. You can do it that way, but the problem of doing it that way is you end up with 2 zeros, because you end up with a positive 0 and a negative 0. So you're wasting one representation for a value that is already represented. But the biggest problem with that approach is you cannot reuse the adder and the subtractor circuit that we have talked about. So we would like to use those circuitry as much as we can. And so here's the idea of back to the subtractors. How do we want to represent signed numbers? So the idea is this. Okay, so when you look at this slide here, the idea, let me point out which part is important here. Two's complement. Okay, so I think I changed the order of the presentation. I just forgot about it. Okay. So what we want to do is to perform the subtraction. So we want to consider the subtraction of 0 minus 1. Keep doing that. So we want to consider 0 minus 1. 0 is represented by 0, 0, 0, 0, and 1 is represented by 0, 0, 0, 1. So whatever this bit pattern becomes using our subtractor would be a good candidate to represent the quantity or the value of negative 1. Does it make sense? Because you have 0, you have 1. 0 minus 1 to us has a value of negative 1. So whatever binary representation is the result of 0, 0, 0, 0 minus 0, 0, 0, 1 would be a good candidate to represent the quantity or the value of negative 1. Is that making any sense? So that turns out to be 1, 1, 1, 1 because of the way we structure our subtractor. So 0, 0, 0, 1 minus 0, 0, 0, 1, 0, 0, 0, 0 minus 0, 0, 0, 1 is 1, 1, 1, 1. 0, 0, 0, 0 minus 0, 0, 1, 0, which is 2, is 1, 1, 1, 0. So these two, this one is a good candidate to represent negative 1. This one here is a good candidate to represent negative 2. So how do we do this? Okay, because this relies on a subtractor, a binary subtractor, in order to figure out the bit pattern. So that's how we get to 2's complement. So this question is, how do we perform this subtraction and be able to do it in a kind of reasonably fast fashion without a binary subtractor? In this representation, W, X, Y, Z are all representing individual bits. Okay, so we are basically saying, okay, I give you a 4-bit number, W, X, Y, Z. How do we find the bit pattern that is representing 0, 0, 0, 0 minus that particular given bit pattern? Are we still doing okay so far? Because I want to do the negation, okay? And I want to figure out, how to do this negation without needing a binary subtractor. Okay, so the way it works is like this. We have 0 minus V, V being the value being represented by W, X, Y, Z, and it should be the same thing as a binary subtraction like this, okay? And I add this one more bit here. There's no space here when there's supposed to be. But this extra 1 does not really interfere because when we do binary subtraction, we only focus on a fixed number of bits. Okay? So by adding that extra 1 as the most significant bit, it doesn't change the least significant bits, the result of the least significant bits. So it doesn't really change the result. Are there any questions between these two rows why I can introduce this extra 1 here without actually changing the result of the subtraction? No questions? Or is that okay? Because we only focus on the least significant 4 bits of the result. That 1 does not affect the least significant 4 bits. Okay? But what is 1 followed by 4 zeros? Well, in binary, it is the same thing as 1, 1, 1, 1 plus 0, 0, 0, 1. Are there any questions about why 1, 1, 1, 1 plus 0, 0, 0, 1 is 1 followed by 4 zeros? Okay? And then what we do is we use the associative law, and we just pull this plus 0, 0, 0, 1 and put it all the way to the end. So now we have 1, 1, 1, 1 in base 2 minus W, X, Y, Z in base 2. So are we doing okay so far with these derivations? Is that okay? All right. Now, this subtraction is special. It is special because it is, first of all, it is dealing with binary numbers. And then the second part has to do with the middle end is 1, 1, 1, 1. So when you look up the subtraction table, okay, 1 minus 0 is a 1, 1 minus 1 is a 0, but neither one would end up with a borrow of any kind. Okay, so let me just kind of write it on the whiteboard here. 1 minus 1 is a 0, 1 minus 0 is a 1. So when you look at the bit that is subtracting and the result, they are just negations of each other, right? So that gives me the ability to substitute a bitwise NOT operation instead of a subtraction operation. In other words, 1, 1, 1, 1 minus WXYZ is really the bitwise NOT of WXYZ. So we end up with the tilde operation, which is a bitwise NOT. So this is how we can end up with 1, 1, 1, 1 in base 2 minus WXYZ in base 2. is the bitwise knot of V, which is the value represented by WXYZ, plus 0001, and 001 is just 1, so that's why we can end up with a bitwise knot plus 1. And that's the definition of 2's complement. It is basically 1's complement plus 1, because bitwise knot is also known as 1's complement. Is that okay?
What's that last sentence you just said? 1's complement?
1's complement is bitwise knot, which is in C and C++ is represented by the tilde
You add the
symbol.
1 to it, it's 2's complement?
Sorry?
Wait.
Yeah, when you add 1 to it, it becomes 2's complement. Yep. So that's how we define 2's complement to be the bitwise knot of a particular bit pattern plus 1. Is that okay? Okay. So the next question is, okay, now that we know how to do negation, it still doesn't really tell us what is the range of values that we can represent given the X number of bits. So what we do in this case is, other than 0, because the negation of 0 is just 0. But for anything other than 0, if X does not equal to 0, the negation of X should not be X. Is that making any sense? Okay, the negation of 1 is -1, which is not 1. The negation of 5 is -5, which is not 5. It makes perfect sense. It's intuitive. The only number where it is its own negation is 0. Okay, so we tried this, with all the different bit values. So we checked it on C2 of 0, and it turns out to be just 0 itself. That's what it is supposed to be. 2's complement of 0001 is 1111, which is not the same as 0001, which is good because we don't want 1 and -1 to have exactly the same representation. So if the representations are different, it is good. Everything works until we work up to 1000, because as it turns out, the 2's complement of 1000 is itself. So in other words, it's kind of like 0, except this is not 0. It is not representing 0. So we have a problem. We know that this is a special value. Is that okay? So that's why, when you draw the number circle, I'm not going to redraw that today because I have it recorded in the previous class. So the key is, this is 0, and 1, 2, and so on. This is 7. This is -1, this is -2, and here's -7. So the question is, what is going to be this guy? Because this is 0000, this is 0111, this is 110, oops. No, it's 1001. Yep, you're right. This is 1001. This is 1000. So the question is, am I going to use 1000 to represent -8, or should it be representing +8? Because it looks like you can choose either one.
Yeah.
Okay? What do you think? It should be -8 because
There's a leading one, and because the range is 2 to the n minus 1, or -2 to the n minus 1.
But why? It's somewhat arbitrary at this point, right? Because we can choose and say that, oh, we want this to represent a quantity of 8 instead of -8. But why do you think -8 is the right answer, is a better answer?
Because it leads with a 1 maybe, and all the other negative numbers also lead with a 1.
Yes, okay, so that's 1, okay, very good. So all of the negative values, when you look at the binary representation of all the negative integers, they all start with the most significant bit being a 1. Because -1 is represented by 1111, -2 is represented by 1110, and so on. And you can see the most significant bit are always 1s when we are representing a negative integer. Okay, so we want to keep that uniform. So we want this to be -8, but there's another reason, okay, which is actually, the consequence of this. Because when you draw an imaginary line like this, we have half the circle being non-negative values. 8 of them are non-negative. 0 itself is non-negative. And then the other half are negative. So in that way, it is actually an even split. Okay? So, because even though we look at this and go like, well, it's not even because one ends with a 7, the other one ends with an 8. It's not even, but it really is even because 0 itself is considered non-negative. So we have 8 non-negative values and 8 negative values. Everything is even. Is that okay? So that's why this bit, the most significant bit of a binary representation of a signed value, is also called the sign bit. If the sign bit is a 1, it is representing a negative value. If the sign bit is a 0, it is representing a non-negative value. And 0 is considered non-negative. Is that okay? All right. So the next topic has to do with, how do we compare unsigned values? Unsigned values are easy to compare because we already have subtraction, right? So after a subtraction, how do you know that the whether the subtrahend, okay, which is XY. We have a subtraction like that, okay, we do it in binary. So after a binary subtraction, how do we know that Y is greater than X? There's one bit that can tell you for sure whether Y is greater than X. What bit are we talking about?
Sign bit.
Not the sign bit.
Most significant bit.
No, not the most significant bit, because the most significant bit is also the sign bit. That's not the answer. This is unsigned, okay? This is dealing with unsigned values. When you're dealing with unsigned values, okay? The borrow, very good. Okay, excellent. So when you're dealing with unsigned values, 0, 1, 1, 1 is representing 7, 1, 1, 0, 0 is representing 12. So when you actually do the subtraction, okay, 1 minus 1 is 1, 1, 0, this is a 1 with a borrow, right?
Yeah.
What does that mean? There's a borrow here, and this is 1, 0, 1, 1, which is 11, right?
Yeah.
What does that mean?
Top is greater than bottom.
It means you got $7 in your pocket to begin with, right? Tech comes along and say, hey, I want $12. You say, I don't have $12. And I say, well, go to the ATM, go to the bank, borrow, right? So you borrow how much? You borrow the next available bill, okay, we got 1, 2, 4, 8, you borrow 16.
Yep.
So now you have 16 plus 7, which is 23.
Yeah.
You got $23 in your pocket before you give me $12. You give me $12, you end up with $11 left in your pocket. But you owe the bank $16. Why did you owe the bank $16? Because you did not have enough money in your pocket to begin with. So the borrow flag all by itself is the indicator that the subtrahend Y in this case is greater than the minuend, which is X in this case. Done. Just look at the borrow flag, you know which number, whether Y is greater than X or not. Okay? So that's what this whole section is about. Okay, and there's a proof too. Okay, so the proof, there's a proof here to basically say, can we prove that the final borrow bit can indicate whether the subtrahend is greater than the minuend or not? Just because it makes sense to us, okay, in the bank, tech borrowing money from you, that sort of thing, just because it is intuitive doesn't mean that it is always right. So there's a rigorous proof here. For those of you who really want to kind of go through the rigorous proof, you can read that part. But if you're not interested in the actual proof, it's okay. This is cisp310, it's not cisp440, so I'm not going to test you guys on proof by induction and that sort of thing, okay? But the bottom line is, the borrow flag is what you use to tell whether Y is greater than X. Is that okay? All right? So unsigned numbers, easy peasy, done. Signed values are more difficult, okay? So you ask the question, how do we know after a subtraction whether the subtrahend is greater than the minuend after a signed subtraction. Now, intuitively speaking, it is actually not difficult, okay? So I'll give you some numbers, not in binary, in decimal. And you can easily tell the pattern. I give you 1 versus 3, okay? 1 minus 3, just using regular subtraction is -2. 5 minus 4 is 1. We got -1 minus -3 is a 2. We got 1 minus -1 minus 4. Yep, this is new. Is -5, and so on. Okay. So what do you think is telling you whether the subtrahend is greater than the minuend or not?
Sign bit.
The sign of the result, right? The sign of the result, if it is negative, if the sign bit is on, that means the subtrahend is greater than the minuend. Okay? If it is not, then the subtrahend is not greater than the minuend. Okay? So there's a pattern to it. So that it seems like the sign flag of the result after a subtraction of signed values represented in binary is sufficient. But there's a problem, okay? There's a problem with this approach. And I'll show you why there's a problem too. It's actually in the notes too. So in the notes, I have -4 versus 5. Okay, so -4 minus 5, and you go like, oh, this is -9, and because the result is -5 is greater than -4. It makes perfect sense. But when you do this in binary using 4-bit numbers, we have a problem. -4 is represented as 1100. 5 is represented by 0101. So let's go ahead and carry out this subtraction. So when you go through the subtraction, what do you have? 0 minus 1 is a 1 with a borrow. 0 minus 0 is 0. 0 minus 1 is 1 with a borrow. Okay, so this is a 1 with a borrow.
Yeah.
And then 1 minus 0 is a 1. 0 minus 1 minus 1 is a 0. And you don't have a sign bit here. You don't even have a borrow here. And yet, 5 is greater than -4. What's going on here? Look at this wheel here. Where's -9? We don't have -9. So -9 is out of the range of signed integers that can be represented in 4 bits. That is why. Okay? So this condition, running out of digits, is called an overflow condition. So this is an overflow. So now that we have a potential problem with the overflow, even though most of the time the sign bit is enough, but when we have an overflow, then the sign bit is wrong. How do we fix this problem? So we have a sign flag, which is the most significant bit. We have an overflow flag, which is an indication that the sign is wrong. Okay? So how do we combine these two and say, oh, okay, if the sign bit was right, it would have been set. How would you say that? If the sign flag is a 0, but the overflow flag is a 1, then it is saying that it's less than. Okay, it would be the same thing as saying the sign flag. If it were correct, it would have been a 1. Is that making any sense? No. Okay. It's all in the notes too, so I'm not gonna read it out of the notes. Okay. The overflow flag is a 1, if and only if the sign flag is wrong. Okay? It's supposed to be a 1, but it is a 0. It's supposed to be a 0, it is a 1. Is that okay? All right. And we know that the minuend is less than the subtrahend if and only if the sign flag is a 1. It makes sense, right? You know, -4, -5 is -9, 5 is greater than -4. So this sign is indicating which number is, whether the subtrahend is greater than the minuend or not. Okay? Okay, so, but we know there's an overflow condition. So how do we combine the overflow condition with the observed, can be incorrect, but observed sign flag to indicate whether the subtrahend is greater than the minuend or not? Or the other way around, the minuend is less than the subtrahend.
Or
Hmm?
use or between the two,
Pretty close.
or just negate S if the overflow is 1.
So what we want is, you know, I'll call this a new flag, is L. Okay, so L flag is a 1 if and only if the minuend is less than the subtrahend. This is what I want. Okay, this new flag L is what I want. Okay, but all I have is the O and the S. Okay, so I want the L flag to be a 1 when what? When the sign flag is a 1, and what about the overflow flag? Okay, if the overflow flag is a 1, it means the observed sign flag is wrong. But if the observed sign flag is a 1, okay, remember what I want, okay? I want to actually, you know, I want the minuend to be actually less than the subtrahend. Okay? The observed sign flag is already a 1, which is indicating the correct result already. Okay? So that means I don't want this to be an overflow condition. So I want the overflow flag to be false. Okay? But there's one more case. What if the observed sign flag is a 0? If the observed sign flag is a 0, but the actual result is less than, that means I want the observed sign flag to be incorrect. If the observed sign flag is incorrect, what is going to be the overflow flag? It's going to be a 1. Exclusive OR, very good. Yep. So that means the L flag, or the less than flag, is basically the sign flag, exclusive OR with the overflow flag. Is that okay? Yeah, I think that part is indicated here. Okay. Then what about the overflow flag? We keep talking about the overflow is basically saying the sign flag is wrong. So how can we tell the overflow flag is wrong? I mean that the sign flag is wrong in the result. What is wrong with this part is right. This is the decimal subtraction is correct. That's not a problem. The correct sign is in fact negative. But the binary subtraction is wrong because we ran out of digits. So the sign of the result is wrong. What is the pattern here? You start off with a negative value, you subtract a positive value from it, you end up with a positive value. Okay? In other words, when the sign of the result is opposite to what it is supposed to be, then the overflow flag is a 1. Is that okay? So, now if we look at the numbers, okay, so this is 4-bit number, this is a 4-bit number, this is the actual difference, okay? The calculation in the middle is not important. I will call this bit x3, this is y3, this is d3 for bit 3 of the difference, okay? How can I say something like this? How can I'm just highlighting the portion, what I want to express. I am subtracting a positive amount from a negative amount, but I got the wrong result because the result is positive. How do I state that? Using x3, y3, and d3. Okay. So in that case, what is x3? x3 is going to be a 1 or 0. Is negative? Is a 1. Okay, sign it is a 1. And y3 is going to be a 0. And what about D3? Yep, okay. So this is one condition where there's an overflow in a subtraction. The other way for the sign flag to go wrong is this one over here. I start off with a positive amount, I subtract a negative amount from it, and I end up with a negative amount, which doesn't make sense, right? So in that case, using the highlighted portion on the projector, what is x3? I started with a positive or non-negative number. What is the sign?
0.
It's a 0. And I'm subtracting a negative amount from it, so that means y3 is a 1. And I end up with a negative amount, which means D3 is a 1. Okay, so these two patterns indicate we have an overflow. Okay, so given x3 is a 1, y3 is a 0, d3 is a 0, I want this particular big pattern to give me a result of 1. How do I make that happen as a Boolean expression? What about x3, y3 bar, d3 bar? Would that do it? Remember the bar is negating. So if I negate y3 and negate d3 and then do not negate x3 and then do a conjunction of these three, this condition will give me a 1. On the other side over here, I would have x3 bar, y3, d3. Right? Is that okay?
Yeah.
So, but both of these are conditions of overflows. Okay? So when you have an overflow, it can be this scenario, it can also be this particular scenario. So what do we do about these two sub-expressions? We have to combine them, but not using conjunction because they cannot both be true at the same time. It's an OR, that's right. So if you OR these two, y3, 3, when you OR these three, that becomes your overflow flag. And then the overflow flag is used in return here, in conjunction with the sign flag, using an exclusive OR to give you the L flag. This L flag in return is the final product. If the L flag is a 1, then we know that the minuend is less than a subtrahend. I mean, just looking at the overarch, just looking at the big picture, is that okay? I mean, do you understand the basic idea of how these flags work? Sort of? Okay. The details are in the notes, okay? So I'm not too concerned about the details because they're all, in the notes here. Because I got the same expressions. Instead of using x3, y3, d3, I use n-1, n representing the number of bits being used to represent the integers. It's n-1 because the first bit is bit 0, so we count from 0, so the last bit or the most significant bit is bit n-1. So the note is a slightly more general compared to the examples here, but these examples will give you an idea of how it works. Is that okay? Okay, we're running out of time, but I do have one final question. I'm kind of surprised that nobody asked me. Maybe nobody wanted to ask me, but this question is floating in your head, all along. What are these flags and what do we use it for? In assembly language, they're extremely useful. Okay, very good. Okay, okay, very good. Okay, but how does it relate to programming? Okay, because just like in the previous class, in 440, I think some of you are thinking about, I just want to learn how to write some games. Why do I need to know all these games and logic and stuff like that, right? Okay, how does it relate?
Your arithmetic.
Arithmetic
Needs you to go overflow the other side, like counts.
Okay. It has to do with control structures in C and C++. has to do with the if, the for, the while,
Yeah.
the do, while, that sort of thing. What about those things? They have Boolean expressions. They have conditions, right? Something that's either true or false, right? Okay, when you look at something that can be either true or false, you will say, well, yeah, but what does that have anything to do with this, right? All of those eventually boil down to what? Comparisons, exactly. And what is this? What are these flags indicating?
Whether it's less larger or greater.
Exactly, it can tell you the ordering of values, right? So if you look at a C++ program, and you look at all the ifs, all the whiles, and everything, the conditions eventually boil down to comparisons. And these flags are basically indicating ordering of values, which can be used as comparisons. So this is the only mechanism, your L flag and your B flag, okay, and also the Z flag that we talked about the other day. Those are the only three mechanisms at the lowest level that your computer can use to make decisions. Should I go this way or should I go that way? Everything boils down to a subtraction and then looking at either the B flag or the C or the Z flag, which is the 0 flag, or the L flag, which we just talked about today. That is the importance of today's lecture, because this is not related to the actual value that we are computing. It has to do with indicating ordering of the values. Okay, so kind of keep that in mind, the big picture, how this fits into the bigger scheme of things, okay? All right, so I will let you guys go, okay? And for those of you who want to spend 5 minutes to get the homework done in the lab, I will be over there. If you have any questions about the current homework assignment, the one that's due today, and you just want me to explain that, I can do that at the lab as well, okay? So that might be important to some people.